Okay, so I think we had just defined, let's see, this is the cursor comes up, right? So we had just defined pressure at a point in a fluid at rest. And now let's go back to the idea of the resulting force on a surface, okay? So we may have gas in some container. And, you know, from time to time, it's nice to consider the molecular point of view to get insight. So we've got a container of gas, and the molecules are just moving around, and they're going to hit the wall. Some may hit the wall and bounce off, right? And so they're exchanging momentum with the wall. And that effect we can measure in terms of the gas pressure, right? But this force exerted on this surface, let's kind of look closely and see what's going on with that. So if we're looking at the molecular point of view, any surface is not going to be entirely flat, right? Depending on the material, and it may be, you know, rough or irregular. And molecules are moving around in all directions, and so some, you know, this molecule may approach with this orientation and hit this surface that's at an angle, and then bounce off and, you know, and go to some different direction, and another molecule may hit this surface, and so it's irregular. But this is the molecular point of view. Now, the macroscopic point of view, we average, you know, we're looking at the average of all of these molecules. And so for molecules that have some orientation downwards, there will be maybe just as many that have some orientation upwards. But the net effect is going to be some force towards the surface. The molecules will impose some force on the surface, and at the same time, the surface exerts a force on the molecule. And so it is this that we're considering. And in particular, in the next chapter, we're going to evaluate the force, say, on this wall due to the pressure, and there may be a distribution of pressure along the surface. So we need to be able to quantitatively evaluate these things. So from the macroscopic point of view, if we look at some surface, and then look at this differential area, so it's just this little section here, will be have a magnitude dA. Okay, so there will be some maybe a height and then a width into the board. Small, so it's a differential area. And you know that areas are defined by their outward normal. So an area is a vector. The direction is indicated by its outward normal. So if we're looking at this surface here, it would be the inner surface inside the container. So its outward normal would be to the left, right? Okay, and that's a vector, the differential quantity, dA. Now, because of this effect here, the effect of the gas on the surface is a normal force towards the surface, as I've already mentioned, but this sort of provides the basis of that. So the differential normal force acting over this differential area is dFn. Okay, it's normal to the surface, and it's always pointing towards the surface. The average effect of all these molecules. And so now, the pressure, recall, is a scalar. But we can evaluate the pressure right at the location of this surface. And so if we know that, okay, and then multiplied by the differential area, so the pressure along the surface multiplied by dA, so force per area times area would give you the force. Now, to account for direction, okay, so force is a vector, so is the area. The area direction is the outward normal. But as I mentioned and as indicated here, the force associated with the pressure is towards the surface in the opposite direction. That's why there is this negative sign. All right? That's very important to remember, but I think very clear here. And then when you want to get the total force over some finite area, okay, then you just integrate the differential force, and so that would be minus integral of P dA. And so this is general over some area. Maybe it's this right-hand side wall, in inner wall, okay? And maybe, for example, if this was water and this was a large tank, there would be a pressure distribution along that wall. Because if it's, even if it's water at rest, there's a hydrostatic pressure variation, right? And in fact, that's what we're going to do in the next chapter. So knowing a pressure distribution along this surface that is submerged in the fluid, we can evaluate the force due to the fluid on that surface through this equation here. And this would be the same also for example, that little sketch that I started off with this today of an airfoil flow over the airfoil will set up a pressure distribution over the airfoil. And, you know, in fact, if it's undergoing lift, okay, that would be primarily due to that pressure distribution. And then one could evaluate the net force due to the pressure using this. Okay? Again, even in moving fluid, the pressure will always act towards the surface. So I want to just spend a little more time on this because this is essential. This is something that we'll use, you know, significantly. Okay. Now, in general, stresses, as I mentioned at the very beginning last time, in general, you're going to have normal stresses. Now, let's say that we have, you know, a body of fluid, and this is a fluid element. So, you know, when we do analysis, we may start with some differential or incremental element, some small rectangular element such as this. And if we look at stresses, stresses are associated with forces acting over areas. And so if we look at any one area of this fluid element, then there's, in general, going to be normal forces. And if they're due to pressure, they would be acting towards the corresponding force, acting towards the surface. But also there's the tangential stresses, which would then produce shear forces across that area. So here, if we're considering a Cartesian coordinate x, y, z, there would be a shear force. So on this area, there would be a shear force acting in the x direction and a shear force component acting in the y direction. Okay? Then a normal force, and it would then correspond to the z direction. So in general, these are the stresses in a fluid that we're going to be considering. And of course, this was only one area. If it's a cubical fluid element, there are 6 sides areas. Okay, but we'll get to that in a little bit. But in a fluid at rest, which is what we're going to consider in Chapter 2, the only stress in the fluid is pressure, a normal stress. But fluid in motion, we know that there may be shear or tangential forces, and we sort of discussed that. This is just the copy of the same slide that we considered that was distinguishing solid from fluid. Okay? And the bottom line was that a shear stress in the fluid, you know, at the interface or within the fluid body is proportional to the rate of deformation. Not the deformation as in a solid, but proportional to the rate of deformation since it continuously deforms. Okay? So we're going to look at this a little further. So so it's proportional to the rate of deformation, d theta dt, and that proportionality is described by a fluid property, which is viscosity. And viscosity, here denoted by mu, mu being the so-called dynamic viscosity, is a measure of the fluid resistance to motion. Okay? Because as I already, I think, mentioned the other Monday or Wednesday, you can have a very viscous fluid. Glycerin, it's very viscous. It has a high dynamic viscosity, large dynamic viscosity. And we know if I had a beaker of glycerin and I let it flow, I poured, it would flow slowly because it's highly viscous. There's greater resistance to motion, greater resistance to the deformation rate. Whereas a lower viscosity, so the beaker filled with water, that water pours out rapidly. I mean, it flows easier, it flows faster. Okay? So to understand this, let me see. What was I going to say about that? Well, we'll take a look here. So we need to understand the nature of viscosity. Viscosity is a very important, significant fluid property because, of course, the resistance to motion, that's really going to affect the behavior of a flow. So let's consider more specifically how it is related to the shear stress and the flow. And the flow we usually describe by the velocity. Here, this expression here, although it is correct for this simple, this is essentially a one-dimensional flow where the velocity is only a function of one coordinate. In this simple flow situation, we have this very simple expression. But to evaluate a shear stress, again, which is important because if you can evaluate the shear stress, you can then evaluate the force corresponding to that shear stress. But evaluating the shear stress, mu d theta dt, the rate of deformation given by this angle here is not very convenient. And we would like to know how this is related to the velocity. Okay, so that's where we're going with this, very simply. Okay, so we can look at this in terms of considering a small fluid element. And let's just look at a fluid element in the plane. And then there would be the shear stress acting at the surfaces of this fluid element. But we could also go back to this configuration here that we just already considered. And just assuming this is a small fluid element, so basically this fluid element could be something like this or a small fluid element within the body of a larger quantity of flow. So we could even take a small fluid element within here. But in any case, so let's consider this this situation here, which we already understand. Okay, and so this point here has, well, let me just go back to the fact that we have a fluid element where we are imposing a shear stress associated with a force. And let me go back and indicate here, we're just considering the xy plane, x in the direction of motion, y vertical. And let's consider this side here, delta y. And we're going to impose a force in the x direction. Okay? And then this will be associated also with a plate velocity. We could consider it delta u. And then within some small increment of time, okay, we considered this deformation angle, delta theta. Okay? So that's the deformation or shear angle. And so this is the starting point. We already said shear stress. In this case, this would be this force, delta F, x, acting over the area. So in this case, it would be a delta x times delta z into the board. Okay, and the shear stress is equal to mu viscosity times d theta dt, the rate of deformation. Now, this angle, okay, we can evaluate the tangent of delta theta as being this distance here, delta L, which is the displacement of fluid associated with the velocity delta u and in this time interval delta t. So this displacement delta L is equal to delta U, length per time, times time. Okay? And then tan delta theta is delta L over delta Y. Okay, so that's this angle. And then we can express the delta L by delta U, delta T over delta Y. But we know that for small angles, the tangent of the angle is approximately the angle. So we replace tan delta theta with delta theta. Okay? And then we divide the delta t out, so it's on the other side. So we have delta theta, delta t equal delta U, delta Y. And then we take the limit as delta t goes to 0 on the left side and delta y goes to 0 on the right side. Here, in this case, so as we take delta t, the limit as delta t goes to 0, then we're talking about getting a quantity that we can evaluate at an instant in time. When we take the delta y goes to 0, remember I said we could also consider a small fluid element in the body of some larger region of fluid. And then we could take delta y goes to 0, delta x goes to 0, and then we shrink it down to a point. Okay? So we already said we're going to take things down to delta v prime, delta volume prime, delta a prime. But now we're just going to assume a continuum, so we can just take limits as delta y goes to 0. Okay? But there's that those considerations that we already did before. In any case, then this is just definition of a derivative. On the right-hand side, this goes to du dy. And then the left-hand side goes to our d theta dt. So this little analysis shows that the rate of deformation d theta dt, it's an angular deformation, is directly equal to the derivative of the velocity, or velocity gradient. Okay? And in this simple problem that we had considered, as it turns out, and we'll confirm this later on when we do differential analysis, we can solve for the velocity distribution in this flow. But it turns out it is linear. Okay? Velocity distributions are not always linear, but for this simple problem, it is. Okay? So we have this linear distribution in this particular case. And so if you know the height of this flow and the maximum velocity, big U, then you can get the linear relation, which is just big U over the height times y. So I think I did that down here. I have it here somewhere. Where did I do that? Okay, here. This is a way you can solve, another way you can solve for the linear relation. But so in this particular flow, and as an example, this velocity distribution is given by a simple linear relation. Okay? And so then, and dependence on y is here. So then we can easily evaluate du dy, the derivative of velocity. And this du dy is the shear. Now, let's go back to okay. So we have this linear velocity distribution, okay? And what I showed is the velocity profile. And I talked about it the other day, but I want to, again, now emphasize what the significance of this velocity distribution is, okay? So this I am, because we're now going to use velocity profiles a lot, especially once we start discussing fluid dynamics. So here's the velocity distribution. So what I am showing is along this vertical line here, okay, at this location, Along this vertical line, the velocity at every point along this line is shown by these, well, is indicated by this line here. So here at y equals 0, so here's the y coordinate, right? At y equals 0, the velocity little u is 0. At y equal this location, the u velocity is this value. At y equal all the way up to h, the velocity little u equal big H. Okay? And so that velocity distribution, which we showed, was equal to this function equal big U over H times Y, is represented by this. Okay? That's the velocity profile. Now, the shear stress at any location Y, okay, can be determined by this expression, mu du dy, and given by the shear, okay, du dy. So we could mathematically and easily evaluate du dy from our linear relation big U over H times Y. So the shear stress for this problem would be big U over H, right? And we can also see that the gradient would be given or indicated by the slope in the velocity profile. Okay? So you might then immediately look at this diagram and say, okay, so here's the slope. And if the velocity profile was like this, then the slope would be steeper and the shear stress would be steeper. No. Because what we're looking at, remember, is u. So this is a plot of u, this line, little u as a function of y. So it's actually y versus little u. But if you're going to if you want to look at the derivative and the slope or the magnitude of the shear, what you want to plot is u versus y. So the slope that you should be looking at is this line, which is this velocity profile reversed and tilted up. See what I'm saying? So you got this velocity profile and you need to reverse it and tilt. So, okay, got that? All right, so let's look at this. We can go back to that if needed. Okay, now, a fluid in which the viscosity, this proportionality constant, where stress now is proportional to the rate of deformation or shear. If this viscosity is not, or the proportionality constant is not a function of the shear stress or the rate of deformation, we refer to it as a Newtonian fluid. And it is then a very simple relation. If you plot the shear stress versus the rate of deformation or the shear, okay, then mu would be the slope. Okay? So for fluids that have high viscosity, then this line here, the slope of, would be viscosity. And this would be a larger viscosity than, say, water or air. Okay? And the fortunate thing is most common fluids are Newtonian fluids. And in this class, we're pretty much going to always assume we have a Newtonian fluid. And then we can use this expression for the shear stress. The dynamic viscosity, FYI, here, the units work out so that, if you just solve for it, it's shear stress over the shear stress being force per area, and then du dy has units of inverse time. And so you can work out the units, and so units of dynamic viscosity are kilogram per meter second. Okay? Now, let's just, to emphasize this, compare two fluids with different viscosities. So we have glycerin, which has relatively high viscosity at the standard condition, 20 degrees C, 1 atmosphere. The viscosity of glycerin is 1.5 kilogram per meter second. As compared with water, the viscosity is 1 times 10 to the minus third. So we're talking 3 orders of magnitude difference in viscosity. So what is the effect? So let's just look at this configuration, the same flow we've been looking at, where we've got a layer of fluid. Here, in this case, it's glycerin. Here, in this case, it's water. We have the lower wall is fixed. The upper plate, we impose a force. In both cases, we impose the same force. We consider the same area, so it's the same shear stress that is imposed in both cases. So we can equate the two, okay? What differs is the viscosity. The glycerin has a much larger viscosity than the water. So then for the same shear stress, the shear or the rate of deformation is smaller in the glycerin than it is in the water. Okay? So what that means then is if you look at u as a function of y, or the velocity profile flipped and rotated, then the velocity, the resulting velocity profile for water is in blue and glycerin in pink. So you can see the glycerin with the higher viscosity has greater resistance to motion, so it would have a smaller maximum velocity than the water. Okay? And so, it now kind of makes sense. And the mathematical description is just right here. Tau equal mu du dy. Okay? Now, just very quickly, viscosity of Newtonian fluids is an in general function of both temperature and pressure, but the dependence on pressure is weak, the dependence on temperature is strong. Yes?
Oil is more viscous than water. Why is it considered usually more slippery? Is that because water has adhesion properties?
I'm sorry?
So oil is more viscous than water?
Yeah.
But usually you think of something drenched in oil as super slippery as compared to
Yeah, oil is used as a lubricant, right? In fact, we are going to, I may possibly give a problem on homework 1, maybe, on that. But there are other properties of oil, that are considered when you consider a lubricant. But I'm not sure if I'm going to answer your question. Let's see, slippery. Let's move on, and then I'll maybe clarify this once we get a little further on, okay? Now, you may need to consider the temperature dependence of viscosity, okay? And it differs, the behavior is different, liquids versus gases. And it's now you go back to the molecular structure. So in liquids, molecules are more closely spaced. There's strong cohesive forces, and there's the resistance to motion is related to these forces. As you increase in temperature, the cohesive forces decrease, and then the viscosity correspondingly decreases. So with increasing temperature, viscosity decreases. And that, for example, think of oil, in that problem. But gases, it has a different molecular structure. The intermolecular forces are relatively weak. The resistance to motion arises because gases, you have the motion of the molecules. And as temperature increases, then this exchange of momentum between the molecules and this random motion of the molecules increases. So as T increases, random molecular activity increases, and this exchange of momentum is also associated with how viscosity works. And later, especially, we'll consider the viscous transport or transfer of momentum between fluid particles or between fluid layers. In any case, the bottom line here is gases have this opposite behavior with respect to temperature. So as temperature increases, viscosity increases. Just FYI, so if you need to account for that and you're given a temperature and you need to look up viscosity, your textbook Appendix B has, so these are the tables that I was referring to. With temperature, you can look up the density, the specific weight, the dynamic viscosity, and also something referred to as kinematic viscosity. So the kinematic viscosity given by the Greek alphabet letter nu. Okay? So the dynamic viscosity, sometimes also referred to as absolute viscosity, indicated by mu. Kinematic viscosity, indicated by nu, is mu divided by density. And then you can work out units. It's meters squared per second. Okay? Now, these tables, you have these tables for water in both sets of units and also air. Okay? But for other fluids like oils, so we have glycerin, we have various oils, SAE 10W, we have mercury, we have octane, kerosene, air, CO2, methane, hydrogen. So you can look up in these figures the viscosity versus temperature, okay, or the kinematic viscosity versus temperature. And if needed, you could back out the density for these various, like an oil here, from this chart. Okay, so these are, just remember, these are all in the back of your, in the appendix, and you may need to use these in homework 1. Okay, so there's that, and then I don't think I really need to. I don't think I need to go over this. Oh, this was this. Yeah, this was a little example problem where you may have a rotating cylinder in a concentric cylinder, outer cylinder, and fluid in between. So if you have this rotating shaft, okay, and it's within, and it's encased in an outer cylinder, and then you want to have a lubricant, you may have oil within this this gap. So if you, so the motion, so you might have some torque or force imposed in this inner cylinder. This outer cylinder may be at rest. So if you unwrap it, the problem could be explained using this configuration, where you have the oil in this gap, you have the wall of the inner cylinder moving at some velocity, so this would be r omega, right? The radius times the angular velocity, and then you can get this linear velocity from it. And then the outer, okay, so actually here, if I blow this thing up, you would see this. The outer cylinder is at rest, okay? And you can approximate the velocity, so, you know, thin gap. So you could approximate it by this linear velocity distribution. And then the question would be maybe here is, what is the force required to keep this plate moving at a velocity u, or moving at this, you know, the angular speed omega? And then you could also then determine the force from the force, the torque. Okay, so I could give you a problem like this on the homework. And if we can assume within this thin gap a linear velocity, you can describe the velocity profile using this big U over hy, and then evaluate the shear stress. Okay, now, so the force of the fluid, oh, by the way, for this linear velocity distribution, you can see that if you evaluate this shear stress, which this shear stress can be evaluated at any location, at the wall or within the fluid, at any location, at any point, you can evaluate the shear stress, okay? And for this linear velocity distribution, you can see that the shear stress is a constant. So if I want to plot the shear stress profile, okay, so this was the velocity profile. The shear stress profile, how the shear stress varies along this vertical, is just a constant. Okay? You can also see that based on this coordinate system, y positive, and starting from the lower wall, y equals 0, up to the upper wall, y equal h. Okay? So y is positive. You can see that if you evaluate the shear, it's positive. So the shear stress within the fluid is positive. All right? Okay. So if you now look at, so everywhere in the fluid, you could evaluate this positive shear stress, and here's the plot. Now, the shear stress is force per area. So you want to identify an area, and then you can determine the corresponding force acting on that area. Okay? So this question then is, so if my left hand is the wall, the moving wall, okay, then I want to determine the force of the fluid on the wall, okay, because what force is required to keep the plate moving? That would be that moving wall is associated with the rotating cylinder. So in general, I may ask you, what is the force of the fluid on a surface? Okay? Okay, so if the surface is my left hand, okay, my left hand, if it's moving to the right, feels a resistance force, right, to the left, right? You just do this and see what your left hand feels, and it's trying to move this way, but there's a resistance force due to the fluid this way, okay? At the same time, because of Newton's second law, the fluid, okay, feels an equal and opposite shear force. So the moving plate is going to move the fluid to the right. So the fluid is going to feel, and that's my right hand, a force, a tangential force to the right. Right? Okay. So this is to explain this detail. So let's just take a look at this little piece of a fluid element that's at the wall. Okay? So at the wall, there's a fluid element, and the surface that is exposed or interacts with the wall is this upper surface of the fluid. Okay? Now, the shear stress mathematically is evaluated in this way, and we said it was positive. Now, in general, shear stress, okay, is force acting over an area. Okay? So that was pretty simple concept. But the thing is, force is a vector and area is a vector. Shear stress in general in 3D is a tensor. And although here it's simplified because it's a 1D problem, so we just have tau equal mu du dy, in general, the velocity gradient is a tensor in 3D, as is the shear stress. And the force in this particular problem, the force is in the x direction. The area, okay, the area would be like the area of my hand, right? The area direction is given by its outward normal. So the outward normal is in the y direction, right? And based on and everything, of course, is defined with respect to the coordinate system. So the force is in the positive x direction. The outward normal of the area that we're considering is in the positive y direction. So this fluid element, looking at the upper surface that is in contact with the moving plate, that's this area, has a force imposed in the positive x direction, and an area normal, the area, is in the positive y. The shear stress is force per area. In this case, the force is in the x direction, the area is in the y direction. The force is in positive x direction. the area is positive x. And the shear stress then is positive, and then that's consistent with this mathematical result of tau equal mu u dy, okay? And so the force associated with the shear stress is in the positive x direction, and so is the shear stress. Okay, and in general, for the general 3D case, there would be subscripts here, 2 of them. This would actually be tau yx. The first subscript indicates the direction of the area. The second subscript indicates the direction of the force. So now that we've, the mathematics is such that the force of the fluid is in the positive x direction, okay? And that made sense because, right, my right hand feels the tangential force to the right. Then there's going to be the equal and opposite force, so equal and opposite to this force on the plate, and that's this. Okay? Now, let's take a look and see what's happening with this bottom fluid element, now that we got that, okay? So if we looked at this bottom fluid element, so it would look like this, right? But now, let's consider the force of the fluid on the lower plate. So this bottom fluid element, the lower surface would be the surface in contact with the lower plate. So what is the force of the fluid on the lower plate? Is it 0 because the velocity, we said the velocity was 0? No, right? Because if the lower plate was my hand and there's fluid moving past, although the one fluid element at the plate is 0, attached to the plate, the shear stress is not proportional to the velocity, it's proportional to the velocity gradient. So the du dy, okay, there is a value of the du dy, and in fact, that shear stress at the lower surface is the same value, right? We already said that the shear stress is constant. Okay, now let's do the same analysis that we did on the lower surface, the surface that of this small fluid element that is in contact with the plate. So we're looking now at this area, and the outward normal now is in the negative y direction, okay? But the shear stress here, the shear stress throughout the fluid is positive because of this, okay? So then, what is the direction of the force? So if the shear stress is positive, and we just said we're looking at an area whose outward normal is negative, for the signs to be consistent, the force in the x direction, or the force caused by the shear stress, has to be in the negative direction, negative x. So the force on this fluid element, okay, on the bottom surface, okay, at the wall, is in the negative x direction. And that makes sense because that fluid element that's stuck to the lower wall, okay, its neighbor, the fluid on top, is moving in that direction. So it's trying to get that fluid element stuck on the wall to move, okay? But it's stuck on the wall, and the wall is causing a resistance force in the opposing direction. That's this direction. Okay? So that all makes sense. Then, if you look at the force of the fluid on the wall, the lower wall, it would be equal and opposite to this force. Okay? So it would be to the right. Again, if there's fluid moving to the right, the lower wall is going to feel that shear force, that tangential force to the right. So that all makes sense, right? So you understand the physics, and you understand the mathematical description of the physics. Okay? So we're going to go over all of this again in Chapter 6, but this is what's going on here in general. Yeah? Question?
In real life, would the sort of circulation of forces that you see in that diagram cause vorticity or flow in like
I'm sorry? So you're talking about this fluid?
in the one below at the box,
He,
kind of circulation of forces, does that cause vorticity in real life that we can see?
wow, vorticity. You are advanced because I think, okay, yeah, we talk about vorticity in chapter, well, okay, I guess, yeah, now, this fluid element, okay, take a look at this fluid element, okay? So we're going to discuss further what happens to a fluid element in a flow. So we already know that it gets deformed, okay? When there's a shear, what was cubical gets deformed like this. And so there's an angular deformation. But when you have a shear, when there's higher velocity here than here, it's also going to rotate the fluid element. That rate of rotation is vorticity. Okay? The fluid element could also elongate in one direction, and in an incompressible flow, the volume remains constant. So if it elongates in one direction, and that's actually a normal strain or normal stress, it has to contract in the other direction or the other two directions, or it depends. So there is this rate of volume change or dilation or dilatation, and then there's just the translation of a fluid element as described by its velocity. So we're going to discuss all of that later as well. It's all related. The vorticity can be evaluated by the velocity gradient, and in fact, it is the curl of the velocity del cross v. Okay, everybody have a good 3-day weekend, and we'll see you guys Wednesday.